Hello everyone. Today we'll learn what is a substituent effect and how can we determine the substituent effect on a reaction through Hammett plots. First of all, before going into deeper details, let's see what is a substituent called and what is this substituent effect. So a substituent is any group on a molecule that is attached to a reactive functional group. For an example, in this slide you can see I have drawn a ketone functional group and next to that we have X, which is a substituent. So this X can be any type of group or molecule, for an example methyl, nitro, hydroxy, even hydrogen. So what is a substituent effect? A substituent effect can be described as when the reactivity of the molecule changes when the substituents are changed. So depending on the substituents in the reactants or solvent should influence the steric conjunction or solvation, leaving group ability, or it can influence the nucleophilicity of the molecule, or basically it can affect acidity, basicity, or variety of other chemical attributes. When it comes to the type of substituent effects, there are basically 5 types of substituent effect: field, resonance, inductive, polarizability, and steric. Now that we know what is a substituent called, we'll look into each and every substituent effect briefly. First of all, we have field effect. So basically the field effect can be arise from a bond dipole or from a formal positive or negative charge. Here I have shown two different phenomena where I have bond dipole or formal positive charge. In either way, because of the bond dipole or the from the formal charge, it can generate an electric field, and because of this electric field, it can actually affect even a functional group which is further away from the bond dipole or the formal positive charge. Second, we have resonance effect. Basically, resonance effect is the ability of an atom or group of atoms to withdraw or donate electron through 5 bonds. In older textbooks, this is also known as mesomeric effect. For an example, here you can see the alkoxy group is inducing a negative charge on this carbonyl group, which is situated quite remotely from the methoxy group. So this is known as resonance. Third effect is the inductive effect. This effect is somewhat similar to resonance, but there's a major difference, because the inductive effect is the ability of an atom or group of atoms to withdraw or donate electrons through sigma bond. So basically, if you have a highly electronegative atom next to a functional group, this can draw electron towards the electronegative atom, and because of that we can have inductive effect. So basically, if we compare the chloroacetic acid and acetic acid, the acidity of the chloroacetic acid is higher than acetic acid. This is because the highly electronegative chlorine draws electron towards the chlorine atom. So another thing is, when the electronegative atom is further away from the functional group, we can observe a decrement in the inductive effect. In fourth place, we have polarizability. In simple words, polarizability is the extent to which the electron cloud of a structure can undergo distortion. For an example, let's say we have a soft compound and a hard compound. So in a soft compound, we can have tightly held electron cloud, whereas in the softer compound where we can have loosely bound electron cloud, and because of that the hard compound is less polarizable, whereas the soft compound is highly polarizable. So here I have sulfide and alkoxide, and if you can see, the sulfide is kind of a soft compound where the electron cloud is loosely bound, and alkoxide is a hard compound. And because of that, if we compare the nucleophilicity and leavingness, sulfide can act as a better nucleophile and also a better leaving group. And if we have nucleophilic attack in both of these molecules, we can see the sulfide leaving quicker than the alkoxide, because the electron cloud is more distorted in the sulfide. Finally, we have the steric effect. So basically, the steric effect is when large atom or groups influence the manner in which the molecule colloid, and also when we have large atoms surrounding the leaving group or the particular functional group, it can prevent the reactant reaching the angle or the depth of collision, which is very necessary for the reaction to occur. So here I have two different examples. In the first case, I have more substitution, and therefore the SN2 reaction is very slower because the nucleophile cannot reach the carbon where the leaving group is. And in the other case, I have less substitution, and because of that we can observe faster SN2 type reaction, because now the nucleophile can easily reach the carbon which is next to the leaving group. Out of these 5 substituents, the first 4, field, resonance, inductive and polarizability, can be considered as electronic effect, whereas the steric effect largely depends upon the size of the substituent. Often in major textbook, it is quoted that trends in chemistry can be explained by either electronics or steric, because sometimes the steric can be considered as a separate effect depending on the size of the substituent. Now we know the different substituent effects. We can have a look at on Hammett plots. So Hammett plots are basically there to picture how the reaction mechanisms vary as a function of the electronic changes induced by the substituents. So from the Hammett plots, a scale has been defined to measure the ability of substituent to influence the acidity of benzoic acid. And so basically what they have done here is they have actually plotted these Hammett plots by using meta and para substituents, using this deprotonation of benzoic acid reaction. So why they use meta and para substitution? Because they wanted to eliminate any possible steric effect associated with ortho substituents, and also they assumed from meta and para position they only have field, polarizability, inductive, resonance effect towards this reaction. And you can also see from this deprotonation of benzoic acid reaction, they actually developed an equation where they compare the reaction rate of benzoic acid with different substituent with the reference reaction where they have hydrogen as the substituent. As I described in the earlier slide as well, the Hammett plot was drawn using this equation right here in the slide. And if you compare the right hand side of the equation, you can see there's two terms, which is the one is the rho, which is reaction constant or the sensitivity constant, which basically describes the sensitivity towards the substituent, which is the slope of the Hammett plot. And also we have a sigma value, which is the substituent parameter. So this substituent parameter is basically depend on the position of the substituent, whether it's in meta position or para position. So what they have basically done is they actually compared the reaction rate. They actually compared all the acidity equilibrium constant for the substituent of benzoic acid to the equilibrium constant for the benzoic acid itself. So as I said earlier, if we have the same substituent at meta position and para position, the sigma values can be different from each other. The reason I will describe in later slides. Now I will describe how the electron donating groups and electron withdrawing groups can actually affect the reaction rate of the deprotonation of the benzoic acid depending on their substitution. So in the next slide you can see how a Hammett plot is drawn for the deprotonation of the benzoic acid considering the electron donating and withdrawing ability. Okay, so let's consider two hypothetical scenarios where you have electron withdrawing group in the benzoic acid and electron donating group in the benzoic acid. So let's see how we can plot this Hammett plot using this information. So basically we all know the electron withdrawing group can draw electron towards themselves, and because of that, if we have electron withdrawing group in meta or para position in the benzoic acid, it actually draws electron towards itself. And in the forward reaction we have carboxylate formation, and because electron withdrawing group draws electron towards themselves, it actually stabilizes this negative charge on the carboxylate. So because of that, the forward reaction is very favorable. That means if you have electron withdrawing group as the substituent, the reaction rate, the forward reaction rate should be faster than the normal benzoic acid. So in that case, Kx should be higher than Kh. And if we plot that in this Hammett plot, we should get positive values for all the electron withdrawing substituents. And if we compare the electron donating substituent, if we have electron donating group in meta or para position, it actually donates electrons towards this functional group, and because of electron donation, it actually destabilizes the formed carboxylate. And because of that, if we have electron donating group, it doesn't actually like to go towards the forward reaction, and because of that we should experience a slower forward reaction, which is the formation of carboxylate. So in that case, the Kx for the electron donating group should be lower than the normal benzoic acid acidity equilibrium constant. And because of that, if we plot that, we should get negative values or values less than 0 for this equation. So if we plot the whole substituent effect, we should get a positive slope for this benzoic acid reaction. So here in this slide I have included a table with different sigma values for different substituents for meta position and para positions. And if you closely look at this table, you can clearly see there are some differences in when a substituent in a para position and when it is in meta positions. So even though the meta position is closer to the ionizing group than the para position, you can see in some cases sigma para values are generally reflect a larger influence of the substituent than their sigma meta values. So this difference is part reflect the ability of the para position to influence the charge at a particular functional group via resonance, an influence that is not possible for the meta position. So in the next slide, I will clearly show you with some example for the sigma para values and sigma meta values why this is the case. So as you can clearly see here, this difference between sigma meta and sigma para is clearly evident with the hydroxy and methoxy groups, And if you compare in the meta position, these groups are found to be electron withdrawing because they have positive values for the sigma meta, and they are actually electron withdrawing towards the highlighted carbon here through inductive effect. And if you compare it with para positions, these groups are electron donating because these have negative sigma para values, and they are actually electron donating toward this highlighted carbon atom through resonance effect. And it is important to note that while this is a resonance effect, it is not resonance with the carboxylate anion. The negative charge of the benzoate anion is not in the conjugation with the aromatic ring, and so cannot be stabilized by the resonance. So in the reaction, next up we have reaction constant or sensitivity constant, which is denoted by this rho value. And actually this rho is described the sensitivity of the reaction to the substituent effect relative to the influence of the substituent on the ionization of benzoic acid. So you can see if we plot the log kx over kh value against the sigma values, we can have different types of slopes in this plot, and depending on the slope of these plots, we can tell a lot of things about the reaction. For an example, here I have shown different conditions where I have positive rho values, and rho value is almost 0, and negative rho values. Let's consider one by one and what these rho values can tell us about the reaction. So let's consider the first case where we have a large positive slope. So here you can see in the plot the slope is positive and it's very larger than 1. So in this kind of slope, you can clearly see the reaction under study is more sensitive to the substituents, and it's actually more sensitive than the benzoic acid. And if you have a positive slope like this, clearly a negative charge is built in during the reaction. So for an example, during the intermediate stage, we can see a negative charge is building in the intermediate of these reactions. In the second case, here we also have a positive slope, but the slope is not larger as in previous case. It's typically in between 0 and 1. And here the reaction is less sensitive to the substituent than the benzoic acid, but still a negative charge is built in during the reaction. So both first and second case where we have positive slopes, but depending on the values of the slope, we can tell whether it's more sensitive to the substituent or less sensitive towards the substituents. So in the third case, the rho value is 0 or almost 0, and if you have a scenario like this, you can definitely tell the reaction shows no substituent effect, and also there's no change in the charge occurs during the equilibrium or the rate determining step. So in simple words, let's say you have different substituent and you are doing the same reaction, and even though you have different substituent, the rate of the reaction won't change depending on the substituent. So basically the slope remained 0 or almost 0. So the final scenario is where you have a negative rho value or a negative slope in this kind of plots. So obviously from the previous knowledge, we know if the slope is non-zero value, that means the reaction is sensitive towards the substituents. And in this case, since we have a negative slope, that means the reaction is creating a positive charge during the intermediate formation. So with that, we have 4 different cases where we have different rho values, and now we know what these rho values means. Since now we know what are these row values means, we can have a look at some examples where we can use Hammett plots to interpret the mechanisms of some particular reactions. So here I have the first example, which is the base-induced hydrolysis of methyl benzoate in water. First of all, let's look at the primary details we have here. So you can see here I have the row value for the rate constant for the base-induced hydrolysis of methyl benzoate in water. And by looking at the row value, you can exactly say it's a positive value, and also it's larger than 1. So it's a large positive value. So from the previous knowledge, from the previous slides, we know if the row is largely positive, that means the reaction is more sensitive towards the substituent. And also from the large positive value, we can actually say during the rate determining step for this hydrolysis, it actually creates a negative charge. So with this information in hand, let's look at the forcible mechanisms involved in these reactions. So as the first mechanism, we have nucleophilic displacement of the methyl group, and as the second mechanism, we have nucleophilic addition to the carbonyl group. So if you compare both the reactions very carefully, you can see in both the reactions in the rate determining step, they are forming two negative charges. So since both of the reactions form negative charge during the rate determining step, we can actually say that row values support either mechanisms, and both the reactions are consistent with the positive row value. In this case, we cannot actually come into a conclusion which mechanism is most probable for the base-induced hydrolysis of methyl benzoate in water. But in this case, from using other techniques, we can actually distinguish the probable mechanism for this reaction. So as my second example, I have here the reaction of dipenyl methyl chloride with ethanol. So the reported row value for this reaction is minus 5.09. So by just looking at the row value, you can tell two things: that this reaction is sensitive towards the substituents, and also since it has large negative value, that indicate a significant positive charge is building during the rate determining step. So by having these details in hand, we can actually have a look at on possible mechanisms. So as the first mechanism, we have SN1 pathway, and as the second mechanism, we have SN2 pathway. So if you compare both rate determining steps, both SN1 and SN2 pathway creates positive charge on the organic structure containing the substituents. And in here, we actually have to look at the magnitude of the row value. If you compare the magnitude of the row value, it's actually very informative because it's very large. So such a large negative row value is consistent with the SN1 like mechanism, because in the SN1 type pathway, you can actually see a carbocation is forming. And when it comes to SN2 mechanism, even though it produces a positive charge, you can see actually there's little or no change in the charge on the carbon undergoing the substitution. So by looking at the value of the row value, we can actually see the most probable mechanism for the reaction of dipenyl methyl chloride with ethanol is the SN1 type pathway. So in conclusion, we learned today that there's 5 different types of substituent effect including field, resonance, inductive, polarizability, and steric. And out of these 5 effects, the first 4, field, resonance, inductive, polarizability, can be considered as electronic effects. So in order to measure the electronic effect in certain reactions, there's some parameters, and we can plot Hammett plots to see how the reaction mechanisms vary as a function of the electronic changes induced by the substituent. So depending on the slope of this Hammett plot, we can definitely tell about the mechanism of these reactions. For an example, here I have stated 4 conditions. In the first 2 conditions, I have positive slopes. So positive slope indicates that we have a sensitive reaction towards the substituents, and also positive slope indicates in the rate determining step in this reaction a negative charge is building. And in the third case, the rho is almost 0 or equal to 0. This means the reaction is not sensitive towards the substituent. Even though we change the substituent, the reaction rate is similar in all the cases. And in finally, we have the negative rho values. This indicates we have the negative slope in the Hammett plot, and this also indicates it's sensitive towards the substituent, but in the rate determining step during the reaction it builds a positive charge. So with this I would like to conclude this video, and I hope you learned something out of this video, and thank you very much for the cooperation.